Hi, this is Mrs. Davis. I am going to do a video or a set of videos for APP Calculus Lesson 1.9 and 1.10 together. They're on the same handout. And there's one homework for it. Okay, so we're going to do a little review just to make sure you remember about rational functions. A rational function is the quotient of two polynomials. So f of x is a polynomial and g of x. So an f of x or a g of x. So both the top has to be a polynomial and the bottom has to be a polynomial. And the only thing you have to remember, well, there's a lot, but just a little bit you have to remember about the domain, right? That g of x cannot be equal to 0 because then you would have an undefined function. So we restrict the domain, and where those values are, where the zeros are for that, is either a vertical asymptote or a hole. So that's kind of what we're covering today. So the gist is vertical asymptotes and holes occur when the denominator equals 0. So we're going to start talking about the difference. So a hole occurs when the factor in the denominator cancels out with the factor in the numerator. So if you can cancel the two binomials out or factors out, then you've got a hole. If you can't, you have a vertical asymptote. So let's look at this first example. I have a x minus 1 on the numerator and an x minus 1 in the denominator. Therefore, I'm going to have a hole at x equals 1. How you figure it out is you say x minus 1 equals 0. So it would be where it equals 0. So x is 1 is where you have the hole. Now you lost your vertical, a vertical asymptote because it was a hole. That's good. So your new function would just be it would be f of x equals x plus 2 with a hole. So a linear function with a hole at x equals 1. Okay, now this is not the graph. This is a different example. G of x is another example. It has x minus 1 cubed over x minus 1 squared. And so if you simplify that, that becomes just an x minus 1. Or let's write it out. We have x minus 1 times x minus 1 times x minus 1 over 2 times x minus 1 and x minus 1. And so you will have a hole. Now you don't have two holes because they're both at the same place. So you'd have a hole at x equals 1 because you were able to cancel out the numerator and the denominator. So this graph just shows you what a hole looks like. You would just put a circle through the function where you're drawing it out, okay? Now also notice that because we have a hole down here, we have to talk about the domain. The domain would no longer be at 1, so you have to include that. All right, and I'll get to this in a second. This is more about the vertical asymptote that's here. So let's look at the vertical asymptote side now versus the hole side. So as you can see in this first example, there's nothing to cancel out, so there's no hole. And so you look at the denominator, and what would that be equal 0? So x minus 1 equals 0, so x equals 1. So if you put a 1 in here for x, you get a 0 in the denominator, and that means that you have a asymptote at x equals 1. And remember, an asymptote is a line, okay, and a hole is a point. A lot of times they just ask for the x value of the hole, but watch out because sometimes they want the whole thing. So in this example, you would have a vertical asymptote at x equals 1. And now for this one, you have x minus 1 and x plus 2 over x minus 1 times x minus 1. Now you can cross that out and you get a hole, but you're also left though with x plus 2 over x minus 1. and you have a vertical asymptote at x is 1. So you can't have both a vertical asymptote and a hole, and the vertical asymptote will win out because there's nothing it could be. It could never be 1. So you have that vertical asymptote, okay? And so let's look at this statement down here. The graph above has a vertical asymptote at x equals 1. So remember, if you're graphing, to always graph in your vertical asymptotes. And then they talk about if I take the limit as I go to 1 from the left, that's what that little negative. So if I'm looking at, I'm going to negative 1 from the left as I draw, I am going to negative infinity. And the limit as I go to 1 from the right, from over here, goes to positive infinity. All right, so that's how you can define a vertical asymptote. You can talk about the limit being negative infinity or infinity. So the same thing here as we go to 1 from the left. And it looks like it should have been, if I go to 1, oh, it's going to 1 from the left. So if I go to 1 from the left, look at that, it's 3. And if I go to 1 from the right, it's 3. So a hole doesn't have any infinity in it. So you need to look at these two limits in terms of a hole here and a vertical asymptote here. We'll do some more examples with that. Okay, so let's look at example 1 actually. It says for each function below, determine the x values of any holes or vertical asymptotes. So we have the crossing out there, and so we can say that we have a hole at x equals negative 3. It just asks for the x value, so we don't have to find the y value. And now we're left with, after we simplify it, we're left with an asymptote, a vertical asymptote at x equals 5. So a vertical asymptote at x equals 5. And let's look at B. Okay, so I'm going to rewrite this as x plus 1 over x minus 2 over x minus 2. And you don't have to write all this out. I just am doing it as I teach you. So x minus 2, there's one of those, and x plus 1 and x plus 1. So we have 2 of those. So I have a hole at x minus 2, all right? Because there was an x minus 2 in the denominator, and I mean x equals 2, not minus 2. So I have a hole at x equals 2, again, because I had the same factor in the numerator and the denominator. And now let's see what's left. An x plus 1 can cancel out. And so you could say at the beginning, okay, I'm going to have a hole at x equals negative 1. And so you're left with x minus 2 over x plus 1. But this is an example where you also have a vertical asymptote at negative 1. So there's no hole. So you have a vertical asymptote at x equals negative 1. And the last one example for this video, if we factor this out, x, we get x squared plus 4, okay? And if you look, you have no hole, so no hole. And if you look at what will make this 0, what will make the denominator 0, this will never be 0. There's nothing you could put in that factor to be 0, but you could put a 0 in for x to get 0. So we have a vertical asymptote at x equals 0. Sorry, at x equals 0. All right, I'll stop this video there.